This podcast is sponsored by Talkspace. You know when you're really stressed or not feeling so great about your life or about yourself? Talking to someone who understands can really help. But who is that person? How do you find them? Where do you even start? Talkspace. Talkspace makes it easy to get the support you need. With Talkspace, you can go online, answer a few questions about your preferences, and be matched with a therapist. And because you'll meet your therapist online, you don't have to take time off work or arrange childcare. You'll meet on your schedule, wherever you feel most at ease. If you're depressed, stressed, struggling with a relationship, or if you want some counseling for you and your partner, or just need a little extra one-on-one support, Talkspace is here for you. Plus, Talkspace works with most major insurers, and most insured members have a $0 copay. No insurance? No problem. Now get $80 off of your first month with promo code SPACE80 when you go to Talkspace.com. Match with a licensed therapist today at Talkspace.com. Save $80 with code SPACE80 at Talkspace.com.
Hi there, thanks for joining us on a Q&A edition, or even a Q&A edition of Space Nuts. My name is Andrew Dunkley, your host. Great to have your company. Coming up this time, we're going to be answering questions from our audience about primordial black holes. This is a what-if question. We love those. Someone else is asking about old galaxies. We are looking for the ultimate Lagrange point and the accelerating universe, which we debunked in the last episode. But we're going to unbunk it on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me again is Professor Fred Watson, astronomer at large, and Professor Jonti Horner, Professor of Astrophysics. Gentlemen, welcome. Thanks for joining us.
Great pleasure, Andrew. Good to be here. Good to have Jonti on board as well, which I'm delighted about.
This is your last show for a little while because you're jetting off to somewhere to look at
well, it's Sweden, Norway, Iceland, and Greenland. And this will be, these tours are pretty regular occasions, as you know, from Marnie's Dark Sky Traveller Company. I do the science, she does all the real work. But this will be the first time we've included Greenland in one of these. So we're hoping for very spectacular views of icebergs as well as spectacular views of the Northern Lights.
Fantastic.
I don't need to get an American visa yet for Greenland.
No, it's okay. Our Mary won't let it go, I can tell you.
Yeah, well, Judy and I are visiting Greenland later this year, so we won't know who's actually controlling.
We'll let you know what it's like.
Yeah, but I've got my US visa exemption, so I should be right. I think. Shall we get straight into it?
Why not?
All right. Our first question comes from somebody who's never sent a question in before except for the other 25 times, Rusty from Donnybrook.
Fred and Andrew, g'day, it's Rusty. A question about black holes. If a primordial black hole, comparable with the size of the Earth, were to enter the solar system at a high angle to the ecliptic and impact one of the rocky planets directly, would it, A, pass through largely unnoticed, B, leave a huge hole through the centre of the planet, which would cause a lot of mayhem, or C, explode the planet completely, or D, none of the above? Happy hunting. Cheers.
I should tell you, Jonti, that Rusty has a habit of throwing curveballs at us. He's always trying to trick Fred. So just bear that in mind when we try and tackle this one.
Well, so I've got a clarification request here, because you get two very different answers depending on minutiae here, because he says it's the size of the Earth. But if it's the size of the Earth, then it's 2,200 times the mass of the Sun. A black hole the size of the Earth. If it's a black hole the mass of the Earth, then it's 9 millimeters across. And so you get a very different outcome depending on which of those it is. I mean, either way, you're going to change the orbits of the planets, particularly the one that it encounters. But if it's the size of the Earth and therefore 2,200 times the mass of the Sun, the solar system will be utterly disrupted. The planets will be ejected. The thing it hits will just kind of be inside it and its mass will have gone up a tiny little amount. If it's the mass of the Earth and therefore 9 millimeters across, we probably wouldn't see it coming. We'd see the orbits changing. It will probably punch a 9 millimeter sized hole through the Earth, but there's not really any friction there to slow it down. So I don't know that you get much in the way of recoil, but you would get a gravitational perturbation changing the Earth's orbit. That'd be my take. So if it came through the Earth, our orbit would become more tilted, seasons would be more pronounced. You'd also have a fairly dramatic change in where the planets are in the sky and all that stuff. If it was 2,200 times the mass of the sun, this will be the last podcast.
Yeah. I think, my take on it is pretty well what yours is, Jonti. I just assumed it was the mass of the Earth we were talking about. And I think it's the radius of the event horizon that's 9 millimeters of an Earth mass black hole. But something that size, I mean, you said in the intro to this, Andrew, that it was Rusty throwing a curveball, and that's what it's going to be. It probably wouldn't be a direct hit because those are quite rare. But it would still be near enough to a direct hit that the orbit of the black hole would, if it came close enough to the Earth, the tidal effects on the Earth itself would be disastrous. One side of the Earth's feeling much more of a pull than the other side. So, effectively, we would still be spaghettified and maybe a bit slower than you would if you just fell into a black hole yourself. But it would be a fairly disastrous scenario, as well as, perturbing the orbits of the other planets. It will be a mess. So I think it's D, isn't it? None of the above is the correct answer for this.
The other bit with the Earth and Moon, though, will be because of the way the Earth and Moon move. If it came through, if it's more than 2 or 3 times the Earth's radius away, we're not going to be disrupted, but we will have big tidal effects. But the Earth and the Moon will be pulled by different amounts in different directions. And so it might be enough to dissociate the Earth and Moon, and suddenly we'll have 5 planets, not 4, in the inner solar system, with the added impact that down the line the Earth and the Moon might collide, and that will be yet another bad day.
Indeed. Yeah. On the flip side, golfers would be thrilled because it would increase their chances of a hole-in-one significantly. Oh, dear. All right, Rusty, thanks for that one. You're always throwing one out there, and that certainly did apply in this case. Our next question comes from Marcel. Science currently holds the belief that our universe is 13.8 billion years old. The James Webb Space Telescope keeps on finding older and older galaxies. Some of the oldest galaxies observed are believed to have formed over 300 million years after the Big Bang. What if we find a galaxy that is 14 million years old? How will we begin to adjust our theories to match reality? Which theories will be first to get thrown out the window versus which theories do we believe are absolutely correct?
Can I have a shot at this? It's not going to happen that we'll find a galaxy older than the universe. It actually, in the early days of the Big Bang theory, that was one of the problems that our measurements then suggested that the Big Bang occurred more recently than the ages of the planets and the stars, that, you have a universe that's younger than its contents, and that's clearly not a possibility. And it was only when we really worked out just how old the universe is, and our current thinking is indeed 13.8 billion years, that was all rectified. But the bottom line is that the yardstick by which the age of galaxies is measured is basically as a fraction of the age of the universe. So you're never going to find a galaxy that's older than the universe, because you're sort of, you're looking back, certainly perhaps 90%, 95% of the age of the universe for some of these really primitive galaxies that we're seeing. But it's never going to be older than the universe, because we define it as essentially a fraction of the universe's age. So that won't happen. What is more interesting is the subtlety of this, which is that we do see galaxies which are seen as the universe was, as it was when it was only perhaps 200 or 300 million years old, which look more mature than we expected them to be. We see black holes that are bigger than we expected them to be, because we thought they'd take a lot longer to grow to their supermassive size. So those are the conundrums. Not that we're going to find a galaxy that's older than the universe, but trying to understand how it is that some of these phenomena that we see, spiral arms, for example, occurred so quickly in the early history of the universe.
I suppose his point was that if we find something that's so close to when the universe began, how do you equate for that?
Well, that's the bottom line, is what I was just saying. It means we have to revise our theories of galaxy evolution, not that we have to throw away the Big Bang, which is what a lot of these questions are aiming at. The Big Bang is absolutely secure. We can still see it. We know that it happened.
And yet we get people questioning us on it, Fred, semi-regularly. There are quite a few people who don't believe in it.
Well, neither did my namesake, Fred Hoyle. He was a staunch believer in the steady-state theory until he went to his grave.
Yeah. What are your thoughts, Jonti?
Well, there's interesting parallels, because the other thing that comes into this is uncertainty, which is we never measure an edge with perfect precision. There's always a bit of an error bar on it. And I'm reminded of the story probably about a decade ago of that star that people dubbed the Methuselah star, which is HD 140283, lovely barcode. And that made news back in like 2013 because people had measured its age. It's an incredibly metal poor star. It's one of the oldest stars in the galaxy for certain. But they'd measured the age based on all these observations of it and estimated an age of 14.46 plus or minus 0.8 billion years. And that age is older than the edge of the universe. So people were saying, how can we have a star older than the edge of the universe? And the subtlety here is in the uncertainty on the measurement, because that plus or minus 0.8 billion years is saying that in 66% of cases, this is one sigma error. So 66% of the time, the age will fall in that age range, and 33% of the time it will fall outside that age range. So that age is compatible with the age of the universe. It's just telling you that this star is very old. It's not saying the star's older than the edge of the universe, necessarily. And what's actually happened in the follow-up from that is a couple of more recent studies have given it ages of 13.7 or 12 billion years. So as we've got more data, the error bar has shrunk, but it's noticeable that that age has moved by more than a single error bar, which is not uncommon when the errors are quite large. Other than that, it is like Fred says, the problem is that even if you change the age of the universe a little bit, these galaxies will still have formed within the first 2% or 5% of its life. You're just stretching the timeline or shrinking the timeline a little bit. It's like what we talked about in the other podcasts. The way that theory and observation interact is that theory is the best possible explanation of what we've already seen, and it predicts what we should see in the future with better instruments. And when those better instruments give us new measurements, that allows us to refine or improve or disprove or kill the theory. There's an argument you can never prove a theory, but you can disprove it. And the more you fail to disprove it, the more confident we are that it's a good theory. And in this case, it's telling us not that the Big Bang theory is wrong. It's not telling us that the universe wasn't formed that way, but instead it's telling us that our understanding of how stars and galaxies form in those early days is incomplete. And that's exactly why people wanted these incredible telescopes to go up there, because that's the only way we can find it out.
And I suppose we have to keep making adjustments for the fact that we've decided all this because of 2 kilos of mush inside out.
Yes, it's amazing what a little bit of gooey carbon can do.
It's the 100 billion neurons in it, the tricky bit.
Yes, that's the. Thanks, Marcel. Great question. Always a good discussion point, that one. This is Space Nuts with Andrew Dunkley, Professor Fred Watson, and Professor Jonti Horner.
This podcast is sponsored by Talkspace. When you're really stressed or not feeling so great about your life or about yourself, talking to someone who understands can really help. But who is that person? How do you find them? Where do you even start? Talkspace. Talkspace makes it easy to get the support you need. With Talkspace, you can go online, answer a few questions about your preferences, and be matched with a therapist. And because you'll meet your therapist online, you don't have to take time off work or arrange childcare. You'll meet on your schedule, wherever you feel most at ease. If you're depressed, stressed, struggling with a relationship, or if you want some counseling for you and your partner, or just need a little extra one-on-one support, Talkspace is here for you. Plus, Talkspace works with most major insurers, and most insured members have a $0 copay. No insurance? No problem. Now get $80 off of your first month with promo code SPACE80 when you go to Talkspace.com. Match with a licensed therapist today at Talkspace.com. Save $80 with code SPACE80 at Talkspace.com.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
And Jonti, we have movement. I see a dog who is coming over to say hello to you. Yeah, what's his name?
That's Maya. That's the sister. We've got a brother and sister who are coming to 8 years old, but she's the more talkative one.
Yeah.
But she's heading off to see if there's anything interesting happening elsewhere.
Yes, fair. Yeah, nothing interesting happening here, that's for sure. Let's go to our next question. This is an audio question from one of our regular contributors. Hello, buddy.
Hello, Space Nuts. Buddy from Oregon again. Hey, guys. Would the center of a galaxy be like the ultimate Lagrange point, like for the galaxy? You were saying if Earth had a tunnel in it, that once you got in the middle, you would be weightless. Is that be like Lagrange point 0? And if so, wouldn't that make the black hole weightless to the galaxy? And would that null point in the center from the Lagrange point create a gravitational well that looked like your donut that you were talking about in the galaxy where the gravitation? All right, thanks, guys. Of the podcast. Keep up the good work.
Got a bit glitchy there at the end, buddy, but that's the internet for you. Thanks for the question. The ultimate Lagrange point, would the center of the galaxy be the ultimate Lagrange point? Who wants to tackle that one first?
I can dive in briefly if you want. So the background here is that the Lagrange points are local areas of increased stability. And it comes out of something called the restricted three-body problem, where you've got in the solar system, which is where I do a lot of my work, the sun and a planet and something else. And that something else is pretty small and tiny. And you can play games. So when I was a kid, I was in Scouts and we used to go out in the countryside and we had contour maps, which were maps of the local area that had these lines on and that told you how high or how low you were. Yeah. And what those contours are actually is telling you what your gravitational potential energy is. It's a measure of the gravitational potential. You can do the same with the solar system. You can make a map of the solar system that is like a contour map. And when you do that, you find the sun's a big well in the middle and the Earth's a smaller well where the Earth is. But there are 5 locations where you have local plateaus, local flat bits. And they're your Lagrange points, and they're more realistically Lagrange areas. And 3 of them are like saddles on a hillside, so they're fairly stable, but if you roll a little way, you'll fall off. And that's Lagrange 1, 2, and 3, and they're on the line between the sun and the Earth. One is on the far side of the sun, one is between the Earth and the sun, and one is just on the far side of the Earth on that line. The other 2 are Lagrange points 4 and 5, which are like these big plateaus that are 60 degrees ahead and behind the Earth in its orbit, or behind Jupiter in its orbit. That's where you get the Jupiter Trojans. And so these are points where the contours are flatter, so you can sit there fairly stable before you roll off in any given direction. The middle of the sun in that analogy isn't a Lagrange point. If that's a slightly different concept. So you are entirely right that if you're in the middle of an object, you don't feel any gravitational pull from that object. More strictly, you feel the gravitational pull from every atom individually, but they all cancel out. So if you're in the middle of the Earth, you're being pulled by people stood in America the same amount as you are by people stood in Australia, but they're pulling in opposite directions. So it all cancels out. So if you were in the middle of the black hole, and ignoring all the other issues that would entail, you wouldn't feel the gravitational pull of the black hole. And if that was exactly at the center of the galaxy, all the mass in the galaxy would cancel out, but you'd still feel the pull from things locally. So if you were in the middle of the Earth and you were massless from the point of view of the Earth, you'd still feel the pull from the moon in one direction and the sun in the other direction. You'd still feel all those things. So you would be still being pulled around. And I dare say that you'd probably be pulled slightly off center if you could move around. And then you'd start to feel the pull from the gravitation of the black hole pulling you back towards the middle. And the further out you go, the more pull you feel, because you only feel the pull from the stuff that is interior to you. Everything, and this used to make my head hurt when we did electromagnetism at uni and trying to get your head around this. Everything more distant from the middle than you are cancels out with everything else. Everything nearer to the middle you feel added up as though it's pulling from the center. So technically it wouldn't be a Lagrange point because it's not one of those plateaus, it's the bottom of a well instead. But it would be a place where you would effectively be weightless, massless. Well, weightless rather than massless as a technical thing. You'd still have mass, but there'd be nothing pulling on you, so you wouldn't have weight. But it wouldn't count as a Lagrange point from my point of view.
Until you turned into spaghetti.
You'd perceive would be the same thing, and it would probably be a lot of pain as you become spaghettified.
Yes.
as you go to get there.
To get there, that's right. So that absolutely, Jonti. I think that means the answer to the question is just yes, except we don't consider the center of things as being a Lagrange point. It's the Lagrange points are quite specific, or areas is a much better term for them, because they're we think of them as an individual point in space, but they're not. They're far from it. And that's why, for example, the L2 point in the Earth's Lagrange system, it can be occupied by many spacecraft at once, which it is.
Yes, and it's not like dead still. The spacecraft have to adjust to the motion.
Yeah, and that's because they're starting to roll off the saddle. So these halo orbits that they move around are actually rolling around the saddle, essentially along a line of constant height, like one of those contours on your contour map. But it's very easy to roll off. So that's why you burn fuel to stay on location. Because with the L2 in particular, if you fall off, you'll eventually fall off properly because you've been pulled by everything else.
Yeah, and land in a pile of dirt, which is what happened when I rolled off the saddle once, but we won't go there. I was not injured.
You're very lucky.
Yeah,
most people do get injured.
Thank you, Buddy. So, as always, I love the way Buddy thinks. He comes up with these amazing ideas. I don't know where his brain is obviously going at 10,000 miles an hour all the time. He comes up with some interesting questions. Our last question today comes from Michael in Evanston, Illinois. Gentlemen, greetings. Regarding the expansion of the universe, it is my understanding that an accelerating expansion means that everything in the universe is moving apart faster and faster. This means that eventually nothing will be visible from anywhere else. Does this mean that the planets in our solar system are moving apart and that our moon is moving apart from Earth due to the universe's expansion? Notwithstanding what we talked about in the last episode regarding a new theory about the expansion of the universe and dark matter, let's stick with the model that we all agree on at the moment. And look, he's right. It is expanding. Everything's moving apart. But there are other factors in play, aren't there, Fred?
Indeed. It's gravity that dominates on the scale of the solar system. We can't feel the expansion of the universe on the scale of the solar system. It's too small. And gravity is the overwhelmingly important force. It's only when you get out to you start looking at objects which are perhaps more than 10, 20 million light years away before you start seeing that expansion. Never mind the accelerated expansion. And even if the accelerated expansion does continue until we get the big rip, which is what some people think might happen, it's going to be a long time before the distance from the Earth to the Moon is affected by that particular geometry. Gravity is the force.
What I've never had clarified for me, and there's all these kind of things, is where that boundary comes. So there is, at the local scale, at the scale of the Milky Way, even gravity wins. So the Milky Way gets held together. The local cluster should get held together as well. But I don't know where the threshold is where it doesn't, because the local cluster is part of a bigger cluster, which is part of a supercluster. And at some point you have this boundary where expansion wins. But if it has to be linked to that cluster structure. So it can't be halfway across the supercluster, because something halfway across the supercluster is still attracted to its neighbors. So it comes down to the voids and everything else. And nobody's been able to give a definitive, essentially, horizon where things will stay closer to us or where things will move away. So I guess we just don't know that yet. We don't have a deep enough, foundational enough knowledge of the structure of matter on that kind of scale near us to know. But I think the eventual horizon is of that kind of scale of the Virgo cluster will still be just about there, but the more distant structure won't. I don't know where that threshold is.
It's probably a very wiggly one, because it's going to follow the inhomogeneity of what we see around us in our local part of the universe. It's a good point that, we can't say, well, beyond 50 million light years, you're going to see the expansion dominating. Because it will depend exactly on the presence. I mean, it throws back to one of the hot topics 20 years ago, which was the Great Attractor. The Great Attractor being this thing hidden behind the Milky Way that we believe now is a part of a supercluster of galaxies that seem to be pulling everything towards it, but it's only in one particular direction. You've got that kind of thing going on all around us and at different distances. So yes, it would be a wiggly, thinking back to those contours you were talking about a minute ago, Jonti, it's a contour, but it's a very wiggly one, I think.
There's a long heritage of this as well. I always love these things where we detect something indirectly, because that's what we do with exoplanets now. It's how Neptune was found.
Yeah.
So we've got several hundred years of inferring that something exists when we can't see it because of its effect on something else. And the Great Attractor is just another in a long list of, we can't see it, but we know it's there because we see what it does to everything else.
The Great Attractor. You enabled me to revive a really old dad joke, but the Great Attractor is the Massey Ferguson, because my uncle used to work for that company, but right off John Deere. And as far as expansion's concerned, expansion wins when you eat too many donuts. You're just feeding me too much information to work with.
Well, this is why I'm gradually resembling Patrick more and more, because I started growing vertically when I was 13, and I've just been expanding horizontally ever since.
Yeah.
Just don't espouse his politics. That's all, Jonti.
Oh no, absolutely not. I lean so far left that I'm horizontal, like many artists.
3, 2, 1.
Space nuts.
Andrew, I was going to say, this is a Q&A session. Can I throw in a question for Jonti?
Go for it. You never ask questions, Fred.
Because I'm not going to be around for the next episode. So I just want to know what Jonti's take on Planet 9 is.
Oh, yes.
It is really interesting. So the first paper I ever published back when I was doing my PhD was debunking one of the many variants of Planet X. And this is a recurring theme that comes up about every 15 or 20 years when we get better data on things that are pushing the limits of our understanding of the solar system. So in the early 1980s, you had Nemesis, which was Richard Muller's hypothesis of a brown dwarf or a red dwarf orbiting the sun on a 26 million year orbit that was giving us comets, causing mass extinctions. And that, even though it sums down now, at the time it was a reasonable possibility as an explanation of the data that made a prediction, which was, if it's there, you'll see it. And then we didn't see it. We got good enough satellites to do it. So that died away. And then back when I started my PhD in 2000, there was a regurgitation of the idea, in this case being Planet X, because Pluto at that point hadn't yet rightfully been demoted. So people still counted it with a grimace. But looking at the data of where comets come in towards the sun from, so not their perihelion, which is where they're closest to the sun, but where on the sky their aphelion would be, they're furthest from the sun, there were suggestions that there was a bit of an enhancement of comets coming from a great circle on the sky. So one particular ring, 360 degrees around the sky, had more comets than any other. And there were two papers identifying this. The twist was that both of them had great circles that were at right angles to each other, that didn't agree. So the first thing I did in my PhD was look at all this and say, well, hang on, our discoveries of comets are biased by the fact that we see them when they're near the sun. We see them at certain months. We see them from the northern hemisphere. There's whether all these different biases, you put them in and both great circles disappear. So it was actually a result of our observational biases. And so that one went away as we got more data. And then what's happened over the last decade or so is that our ability to find small objects in the outer solar system has got better and better. So we're starting to find things out beyond the kind of nominal edge of the Edgeworth-Kuiper belt, beyond about 50 AU. And these are objects that are far enough away that the influence of the planets isn't enough to modify their orbits in any real sense. But there has been a set of detections of objects further out that, a bit like that great circle, appear to be more likely to be found in one part of the sky than anywhere else. Now, one explanation for that is that there is something that we haven't seen that's further out that is stirring them up and has corralled them. And that works really well to explain what we see. Another explanation is that this is an artifact of the observational bias, because the survey is primarily done by the Canada-France-Hawaii telescope, which sees northern hemisphere sky by preference to southern hemisphere, has a varying cycle of cloudiness through the year. It's harder to find these things where the Milky Way is. So there are some people arguing that this will turn out to be an observational bias. You've also got a few different versions of Planet X being proposed. So the most famous one is the one that gets talked about a lot, which is Batagin and people like that, talking about a fairly massive Planet X. But a really good friend of mine who actually visited me at UniSQ a couple of months ago, Patrick Sofia Lukaf from Japan, has been quietly running simulations looking at an Earth mass object, which would work from the point of view of our understanding of the formation of the giant planets. You would have formed a lot of objects that size that were then ejected, that weren't incorporated, some of which will have been ejected but not fully ejected. So you could have Earth-sized objects in the Oort cloud quite reasonably. And he's been looking at the distributions of all these things beyond Neptune. If you had something the mass of the Earth 200 or 300 or 400 AU away, that we couldn't currently detect but we'll be able to find in the next 5 or 10 years. And that does a really good job of explaining the groups of objects we can't currently explain. Doesn't mean it's right. What it's doing is saying, here is something we can't explain observationally. Here's a couple of different teams proposing hypotheses that do a really good job of fitting the data and explaining what we otherwise can't do. And they then make a prediction in both cases, which is as Vera Rubin comes online, this incredible new observatory that's going to increase the number of objects we know by a factor of 10 to 100 times in the solar system. We'll certainly have a lot more data. And if these theories are correct, these data will support them. If not, they'll shoot them down. Now, I think given the past history of Nemesis and Planet X, people are understandably very skeptical, but it's very good science being done by really reputable scientists who are not saying this is definitely there. They're saying, here's something we cannot explain. Here is one way of explaining it that works really well and fits with the observational constraints we currently have. The truth could be out there, it's kind of X-Files thing. But we won't know until we get more data. When that data comes in, this is what we should look for. And that's really important because if you do some modeling, and some solar system groups have done this in the past with very famous models, that explain very well what we currently see, but nothing else. They don't make predictions of what we don't currently see. Then that to me is stamp collecting. It's not actually science. Because there's an infinite number of ways of explaining what we currently see. And what both these models are doing really well is they're explaining what we currently see, but also predicting what we will find in the future if their model is correct and if their model is not correct. So they're testable hypotheses. And that's really important because that shapes how we do our future science, what we look for. So I find it really exciting. I'm, really keen to see what happens with the various iterations on Planet 9 over the coming decades. And if it dies down, I'm sure that in 20 or 30 years, when we get the next generation of telescopes, the idea might come up again because we're looking at this ever-growing circle of knowledge around the solar system, but it's not that big yet.
So the 5 minutes you just spent on that could have been answered with a maybe.
With a maybe. But I think it's important to clarify that this is good science, because it does sometimes get passed off as a bit of a joke because there's a past history of things falling flat. And those things that fell flat were also very good science. It's just, this is the way science gets done. And it runs counter to the opinion that a lot of people get when they come out of school because of the challenges of the curriculum, that science is fact and is science sealed and delivered. And it's one of the problems we've seen with accepting that cigarettes cause cancer, accepting that climate change is an issue, is that people get taught that science is signed and sealed and delivered, and then when things change, like Pluto is demoted, that feels like a betrayal. It feels like you've been lied to, that somehow things nefarious are going on. And it makes it much harder then to get changes in our understanding through. And so it's really important to stress that this is how science works, and this is really good science.
No, fair point. Great point. Very good. Very good. Gents, that's where we're going to have to finish up. Thank you so very much, Professor Fred Watson, and enjoy your travels, and we will catch up with you around late February by the look of it.
Sounds like it, yep. Thank you, Andrew. Thank you, Jonti, and I look forward to listening to Space Nuts podcast without being on it.
That would be rare. Yeah, that's just plenty of photos. Okay.
Yes, please do. And Professor Jonti Horner, thank you for being a part of Space Nuts Q&A today as well. We'll catch you on the next episode.
It's a pleasure. Thank you for having me.
And thanks to Hugh in the studio, who couldn't really do much because he was caught in the ultimate Lagrange point. And from me, Andrew Dunkley, don't forget to send us your questions via our website, spacenutspodcast.com, spacenuts.io. Get your questions in. We'll get to them as soon as we possibly can. So from me, Andrew Dunkley, thanks for your company. See you again on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.